as usual, I've got a number of projects on the go. One of them's a CW rig, and another one requires FSK. And as we all know, FSK and CW signals can create key clicks, and that's undesirable. Modern radios, and certainly all the commercial radios, employ a method called a raised cosine function that gradually turns on and off the keyer envelope at the beginning and end of a transmission. So that's what I'm going to talk about today, and how I intend to implement it. Now, fortunately, both of my projects are using a Teensy 3.2, and luckily for us, a Teensy 3.2 processor has a DAC output on it. So I'll be using that output to drive the PA circuitry. But I'm not talking about the PA hardware today. I'm just going to look purely at the software. Now, if you want a proper explanation rather than listening to me ramble on, the best I've been able to find, and is absolutely superb, is the documentation on the QRP Labs website for their little 5-watt PA. And the diagrams I'm about to show you come from that documentation. So let's just refresh ourselves about sine waves, which is the blue line, and a cosine wave, obviously just shifted by 90 degrees. Now the raised cosine profile is essentially that profile, but flipped or normalized to look like this. So you're raising from 0 up to a maximum, and then back down from a maximum down to 0. So that's the raised cosine profile that we're looking at. So that section there would be the beginning of the transmission, and that would be the fall off at the end of a transmission. So I've chosen to implement it in this way. So I'm going to ignore cosines because all I'm really interested in is that part of the curve there. That'll be the downward transition, and then if I reverse the number sequence and start there on the beginning of a transmission, so those will be the two curves that I'm interested in doing it. And how I've chosen to implement that is, first of all, generate a sine table and store that sine table in an array. And I've chosen the array to be 120 bins. So it's 120 bins wide. So half of 120, so it'd be 60 there, 30 there, and 90 there. So I've got 160 bins worth of information explicitly defining 30 points on each section of code. And the bits that I'm interested in, the bins that I'm interested in, are between 90 and 30. So when I come to transmit, I'll load bin 90 into the DAC and decrement each step until I get to bin 30, and that will be the maximum output from the DAC. And likewise, when I'm coming to finish the transmission, I'll input bin 30 and increment the bins until the end of the transmission till we hit bin 90. And if we put that at the beginning and end of say a CW transmission, we'll end up with something that looks like this, where normally we'd have a hard turn on here, and that's the area that causes the clicks. Totally undesirable, and that would be the off. And again, that's the area which we want to avoid. So we'll start the transmission, implement the raised cosine coefficient on the output of the DAC, which will subsequently gradually increase the voltage to the PA. And then at the end of the transmission, we do the reverse, and that's ultimately what we're looking at doing. So jumping into the software, we'll need to declare a few things. The speed of the ramp, we need some method of slowing it down, because I mean these teensies run at 96 megahertz, and we need that ramp to be in the order of 10 milliseconds from minimum to maximum. So this usec variable I'll be using to create that delay. As I mentioned earlier, our sample depth, or our DAC depth, sorry, our sine table depth will be 120 samples. So our DAC buffer is declared with that end sample rate. So now, once we've declared those, the first thing we need to do is to actually generate the sine table, and I've chosen to do that within the setup area of my code. So within setup, ignore all the rest of this at the moment, but to actually load the sine table, and it's one complete cycle. We're entering a loop, and that loop is the sample depth of 120. We're creating a float variable here, which is based on what sample we're looking at, and then we then fill that DAC buffer position with this calculation. Now we're looking at a 12-bit DAC on a Teensy 3.2. So a 12-bit DAC, it's 2 to the 12, so that's 4096 as the maximum integer number. So 4096 is the maximum we can push into the buffer. This calculation will give us a maximum of 4000, which is close enough. So I'll have a normalized sine table from 0 to 4000 in a format ready to just push straight out to the DAC when we need it. And then just down here, I've created a series of print statements that we can look onto the serial monitor. I'll upload the code, and then we'll see the serial dump, and there we go. So the first sign table, don't forget, so the first bin data, second bin likewise, all the way through to bin 110. So 120 bins to play with. And if we look at the data for the ramp, the rise ramp data, starting at bin 89, we slowly increase as we decrement all the way down to 4,000, and the fall data, starting at 31 and incrementing, we drop it all the way down to 0. So there's the two ramps that we'll be using to actually generate the DAC output when we require it. So we'll dive back into the other section of code again. Okay, jumping back to our runtime code. Every time we want to drive the keyer output, which ultimately goes to a FET, which grounds the keyer output, every time we drive that high, we want to start the ramp. So we drive it high, enter this loop. Bearing in mind we're only interested in a portion of that sign table, the rise portion of that sign table, from bin 89 to bin 29, and for each loop of this, each loop from there to there, we are incrementing the DAC buffer. We're decrementing the DAC buffer until it reaches 29, and it falls out of the loop. Now within this loop here, remember earlier on I was telling you, describing we needed to slow this down, so the rise time was approximately 10 milliseconds. Well, we're playing around with 60 bins here. Now 60 divided by 166 microseconds, 60 times 1.166 microseconds will give us 9.9 milliseconds, which is close enough. So this is our delay, and each time it sits here until microseconds hits 166, and then it resets that, loads the next buffer in. So the DAC output is incremented every 166 microseconds. And we do exactly the opposite when we need to turn the keyer output device off, but we need to decrease the curve before we actually turn the keyer off. Exactly the same, but we're using bins 30 to 91, but this time we're incrementing them with same delay. So when you actually look at the output on the scope, we should see the MOSFET pin being triggered high to low instantaneously, but the DAC output following that, but introducing the raised cosine rise profile, followed by the DIT or the DAR duration or FSK information, and then falling with the raised cosine fall profile. So let's have a look at what that looks like on the scope. Okay, let's have a look what it looks like on the screen. Right, quick explanation. The yellow trace is the keyer output, and as you would expect, it's a hard on-off trace, and the top trace is the output from the DAC, and there's slope, a rise slope and a fall slope. And if we zoom in on that, you can see quite clearly that we've got a nice rise profile on key on, and a nice fall profile on key off. So that's the software working. All we need to do now is to knock up some hardware for a PA and make sure it all works on and check the actual transmit envelope. But that's a subject for another video. Hope you've enjoyed 73.